I'm Phil Kaaret, and I'm going to tell you about some recent results on the CGM of the Milky Way as seen in X-ray emission obtained with the HaloSat CubeSat. These results were recently published in Nature Astronomy. So HaloSat's pretty small. It would fit in your overhead luggage, but it has a very large field of view, 10 degrees across, which makes its grasp competitive with that of the major X-ray missions. So over the course of 2 years, we performed an all-sky survey with HaloSat tiling the sky shown here in galactic coordinates with 333 fields, and we'd acquired 3 spectra, one for each of 3 identical detectors for each pointing. And so we then fit those spectra obtained in the 0.4 to 7 keV band with a model. One component is that in that model is optically thin thermal plasma for the halo emission, and the free parameters of that component are the emission measure and the temperature. So this shows a map of the emission measure for the southern halo, be less than -30, and the emission measure is just the integral along the line of sight of the density squared of the hot X-ray emitting material. So you can see, even just from the color bar, that the emission measure has large variations over a factor of 10. It's also clumpy. The adjacent points are pretty well correlated, but when you go to larger scales, there are definitely non-smooth variations, and there's an overall trend that it's brighter towards the galactic center. Temperatures are actually consistent with being constant at about 0.23 keV. We took those emission measures, shown here as the points with error bars as a function of angle of the center of the field of view from the galactic center, and then compared it to models of the density distribution of the hot gas. So the blue curve here shows a spherical beta model, while the yellow points actually show an empirical disk model, where we assume that the density of hot gas was proportional to the surface density of star formation, and to trace that, we use the measured surface density of molecular hydrogen. And so this empirical disk model offers a highly significant improvement, F-test of 3 × 10⁻⁶ relative to the spherical beta model. We include as a parameter the scale height of the X-ray emission, and when we fit for that, we get a very relatively small value, about 1 kiloparsec, including systematic error. That could be up to 2 kiloparsecs. This means that the soft-ray X-ray emission is dominated by disk emission near the galactic plane. But our disk-only model underpredicts other measurements, such as oxygen 7 absorption line measurements. And so to bring agreement with those, we can add an extended halo component into the model, which makes us agree with those measurements and the HaloSat measurements, but that extended component only contributes about 10 to 20% of the total X-ray emission that we observe, depending on the field. So to conclude, the soft X-ray emission from the CGM of the Milky Way is clumpy with large variations. This clumpiness is naturally explained by local variations in star formation. And the soft X-ray emission should be an excellent tool to study feedback in the Milky Way. And this is a link to the paper that came out last November in Nature Astronomy. And I'll just conclude with a slide of some of the people who've contributed to the mission. Thank you.